Big M is molarity, which is moles of solute divided by liters of solution is really the true definition of what molarity is. Molarity is big M, which is moles per liter. So oftentimes when we talk about something being concentrated, what we're a lot of times referring to is the molarity, which is the concentration of it. And that's the most common sort of unit of concentration as you see with solutions. And really it's the top part here. So if something is really concentrated, it has a lot of moles of solute. So it has a lot of the solute dissolved in it. So remember that a solution really is, as we talked about, two things. It is the solute, which is the smaller part, and it is the solvent, which is the larger part. Thank you. And so, for example, if you had, say, a 18 molar hydrochloric acid solution, actually, we'll just do sodium chloride solution. We'll do sodium chloride. What that means is pretty concentrated, because basically what that means is you have 18 moles of sodium chloride per liter of solution. And that would be in comparison, say, to if you had, say, like 0.8 molar sodium chloride solution. What that would mean is you have 0.8 moles of sodium chloride in a liter of solution. So they're really the same volume, right? A liter of solution, 1,000 milliliters. This one has a lot more of the solute dissolved in it than this one. So this would be considered concentrated solution. This would be considered a more dilute solution. So in a more dilute solution, you have a lot more solvent in this case. So you would have a lot more water in this case than you would of the actual solute that's been dissolved in, like the sodium chloride, for example. So really like a lot more water molecules than the sodium and chloride ions floating around in there. So if you kind of just visually maybe looked at it in this guy, you would have, a little, if these circles were the sodium ions and the chloride ions, you would have maybe some of those floating around in there. As opposed to, say, this guy, and we'll assume this was the same volume, you would have a lot more of those ions basically floating around in solution, right? So it's a lot more concentrated. So that's really the difference when we kind of talk about concentrated and dilute solutions. That concentrated solution definitely has a lot more of the solute dissolved in it versus a dilute solution, which has a lot more solvent. And really, as we'll talk about, how you go from like the 18 molar guy down to this guy, which is the more dilute solution, is in a lot of cases, the only thing you're going to add is water in a lot of cases. And when you add more water, what you're basically adding is more solvent. And if you think about what molarity is, for example, that means that really the only thing you're increasing is the liters of solution. And that's why the molarity comes down, because you have, again, a lot more water than you do the guys actually floating around in there. So that's like really the kind of the difference. You can even go back to like your like the sugar sort of example. If you just put like one packet, right, of sugar, say, in your water, maybe you taste it, or like your iced tea or something, maybe you taste it or you don't taste it. But if you took like, the Costco size thing of sugar and just kind of dumped it in there, right, and dissolved as much of that sugar in that your drink as you could, you definitely would taste it probably a lot more. It'd be a lot stronger, right, because it has a lot more, say, sugar dissolved in it. So that's kind of the difference between concentrated and a dilute solution. Really, again, the main difference is the amount of solvent. The dilute solution has a lot more solvent than the more concentrated solution. And by that measure, that means the more concentrated solution has a lot more solute than the more dilute solution does. Now, in terms of saturated and unsaturated, those two are usually sort of talked about together. And you can get definitely a more concentrated solution when you hit a saturated solution, because again, what that basically means is that's the maximum amount of solute you could get to dissolve. And unsaturated is you have not hit that maximum amount. So you could kind of draw a comparison to concentrated and dilute solutions, kind of the same idea. You know, if you loaded your drink with a bunch of sugar and you basically got the max amount of sugar that will dissolve in there, it's going to be a saturated solution, right? And at that point, if you tasted it, it would be pretty concentrated in terms of the sugar that's in there. And vice versa, if you had an unsaturated solution, maybe, you know, you didn't necessarily hit the maximum amount. So it'd be a little bit more dilute. But, you know, in terms of concentrated and dilute and saturated and unsaturated, those are sort of the comparison. Concentrated and dilute kind of go together. Saturated and unsaturated go together. Because remember that you could, in theory, right, if you take the sugar example, you could dump the sugar in, right, and stop right before you hit, you know, the saturated point, and you would still have a pretty concentrated solution, right? So, you know, there's not necessarily that direct tie-in to it, but, you know, if you just put a little bit of sugar in there and stopped, you definitely have an unsaturated solution. It'd probably still be dilute. But if you got yourself close to a saturated solution by dumping the sugar in, you may not have hit a saturated solution, but you still have a pretty concentrated amount, right? If you're just like right below that line, stuff like that. So there is a slight difference between those two. Other questions on stuff that I could answer on anything we've been talking about? So again, when we come back, we will have a quiz on naming and drawing on Monday. And again, pretty much everything reaction, equation related, and grams, moles, and stoichiometry on Wednesday, which is chapter 7. Any stuff that I could help you with, or gas stuff that we've been talking about that I could help you with? Also, in a few weeks, right? The homework should be due, so make sure you know you've been working on that. At this point, you should be able to finish all the homework for exam 2 at this point. Yeah, so everything we've talked about. Any questions? Type 2, naming type 2. That's type 2. Yeah, sure. So let's talk about type. Well, let's talk about type 1 and 2. How's that? That way we could do the comparison of those two. So type 1 and type 2 compounds, they're basically both the same type of compound. They're both ionic compounds, which means that they basically have a metal and a non-metal together. So that is the first thing. Remember that sort of when you're doing naming and all those things, that's the first thing you want to really recognize is, you know, what you're dealing with. Is it a metal and a non-metal, which would make it an ionic compound, and most likely would make it one of these two types of situations. Whenever a metal is involved, especially with naming and all those things, it is always the most important thing to look at. So definitely, if you have a metal involved with a non-metal, you have a metal involved with a polyatomic ion, as soon as that metal is involved, that is the one thing that you really want to look at. It is really the one that determines how you name everything, is the metal. So the metal is really the most important thing. The metal should always be the cation, which is the positively charged ion. The non-metal is the anion, which is the negatively charged ion. So in terms of a type 1 compound, because the metal is always the important one to look at, that is the one that we would want to focus in on. And what makes it really a type 1 compound is the metal basically has a fixed positive charge. So those guys have a fixed positive charge. And the ones on the periodic table that have a fixed positive charge is anybody basically from group 1 on the periodic table, group 2, group 3, which is basically aluminum. And from the transition metal region, it is zinc, which when it does create a charge will be +2. It is cadmium, which also when it forms a charge would be +2. And it is silver. So if you come across a compound that basically has any of those metals in it, it's going to be a type 1 compound. And the way that we name type 1 compounds is we always use the whole name of the metal. And this is regardless of how many there are of it. We just simply use the whole name. And it's the nonmetal that gets the IDE at the end of it. So we draw kind of the last part of the name of the nonmetal and we replace it with the IDE. So for example, if we had CaCl2, like we saw earlier, we would want to look at this and first identify calcium as a metal, Cl, which is chlorine, which would be a nonmetal. So again, that tells us this is an ionic compound, and we're going to always focus in on the metal. And when we look at calcium, that is group number 2 on the periodic table, which means, frankly, it has a fixed positive charge. And in terms of naming, that's really all you need at that point. Once you identify that that thing is a type 1, you just roll with how we name it, which is, again, we would use the whole name there of the metal, which would be calcium. And regardless of how many nonmetals there are, it still just gets the IDE. Again, no prefixes or anything like that. So this would be chloride. And remember that the cation would actually be calcium with a +2 charge in this case. The anion would be chloride there, or chlorine with a -1 charge. And that's why the 2 is here, right? The 2 is here because whenever we put anything that's positive and negative together, it needs to equal 0, right? So basically, to put these guys together, we need a -1 and a -1. That gives us a -2 to balance out the +2 that is there for the calcium. So if we look at another one, for example, like do like Al2O3. So we look at something like this. So we see Al, which is aluminum, which is a metal. We see O, which is oxygen, which is a nonmetal. And once again, we're going to focus in on the metal, which is aluminum. And if we look in the periodic table, aluminum is group 3, which means it has a fixed positive charge. So once again, that tells us it's a type 1 compound. And that means we use, again, the whole name here of the metal, which would be aluminum. And again, regardless of how many oxygens there are, it just gets the oxide. Again, no prefixes on either. The aluminum here has 2 and the oxygen has 3. It has no effect on this type of naming, and that is exactly how you would name it. The cation here is the positive guy, which is aluminum. That's group 3, that has a +3 charge. The anion in this case is oxygen, which is group 6. It has a -2 charge. So that's why we do again have these numbers, because when we put it together, we need to equal 0. So the common number between 3 and 2 is 6. You just get that by multiplying them together. 3 times 2 is 6. So to get the oxygen to 6, you actually need 3 of them, which is why that 3 is there. And to get the aluminum to 6, you actually just need 2 of them, which is why there are 2 of them. But it has no effect on the actual name when you name it. Any questions on like that type 1 type of thing? Yeah. Now, type 2, which is what you asked about, is again pretty much the identical situation. You're going to have, again, your metal and your non-metal. But the difference here is the metal will have a variable positive charge. And it is, again, always the metal that's important here. And the way you can recognize that it is a type 2 is that metal will be a transition metal. Or just to the right of it on the periodic table, where you see something like tin or lead in that sort of area, it's kind of like below the staircase there that comes down, is also, although they're not transition metals, they're named the same way. Now, because they can have a variable type of charge, basically naming is all about telling people kind of like what you're dealing with, what you're using. So because it can have a multiple charge, we do have to kind of include the charge in the actual name, not in the formula, but in the actual name is how we have to do that. So it works kind of the same way as type 1. We use the whole name of the metal. We still finish with the non-metal that, again, you drop the last part of the name and put the IDE. But the thing that distinguishes this from a type 1 that it is a type 2 is we do need to include a Roman numeral. And again, it's really important and oftentimes misunderstood. The Roman numeral is not how many metals that you have. It's actually if you just took one of the metals out by itself, what the positive charge is on one of them. So what the actual positive charge on one of the metals are is what that Roman numeral represents, the positive charge on one of the metal ions. So in these cases, because these metal guys can basically make different types of positive charges, you basically have to use the Roman numeral to tell people, okay, in this case, we're talking about the guy that makes the +2 charge, or in this case, we're talking about the guy that makes the +3 charge or +4 charge, because it's not like a known thing like in type 1. So like in type 1, when we see sodium in a formula, because it only could be +1, no matter what the situation is, you don't need to tell people, hey, it's going to be +1 in this case, because that's really the only type of charge it could have. But when we're dealing with something, say, like iron or something like copper, which is a transition metal, in some cases, it could be +2 or +3 for the iron. In other cases, for copper, it could be +1 or +2. So you have to kind of tell the people, like, in this case, we're dealing with the +2 guy, but in this case, maybe it's the +1 guy, because it's just not known by looking at the formula that, hey, which ion it is, if you're not sure. So the good news, though, is you will always know what the charge is on whatever it's attached to. So whatever that metal is attached to, you will definitely for sure know the charge on it. So you could kind of work your way backwards to figure out what the positive charge is on the metal. So for example, speaking of copper, if we had something like CuO in this particular case. So the first thing we would approach this is the same way as we approach anything else. We would see Cu, which is a metal. We would see O, which is a non-metal. So that tells us it's an ionic compound. And again, we would focus in on copper, and we would see copper right there, kind of in the center of the transition metals. So that automatically would tell us it's a type 2 compound. So once we figure out that it is a type 2 compound, we want to go to the part of, I want to figure out what the charge is. So in this case, copper could be like +1 or +2. So we want to really figure out in this specific case what the charge is. And that means in this situation, we would then want to look at the nonmetal that's attached to it. And when we look at the nonmetal that's attached to it, it is an oxygen. And we know from the periodic table that group 6 is always going to be a -2 charge for things that are nonmetals. So we know for sure that this oxygen has a -2 charge because, again, on the periodic table, right, everybody in group 1 is +1, group 2 is +2, group 3 is +3, which is aluminum. We skip group 4. Starting with group 5, which are nonmetals, is -3, group 6 is -2, and group 7 is -1. So there's like the staircase that kind of comes down here. So those are sort of fixed sort of charges that we do know on the periodic table. So since oxygen is -2, and we know whenever we put something that is positive and negative together, it needs to equal 0 in the simplest way possible. So in this case, the simplest way possible for this to equal 0 is the copper would have to have a +2 charge to balance out the -2 that's on the oxygen. So when we take +2 and -2, it equals 0. Once you sort of determine that, you have everything that you need to actually do the name. So the name here would be the same idea. We're going to use the whole name of the metal, which would be copper. Now, here's where the Roman numeral comes in. It is the charge, not how many you have. So the charge on this guy is +2, which means the Roman numeral here should be 2. And again, that is for the actual charge that you see on it. And in this case, we would just use oxide like normal here. Yeah, so that would be copper 2 oxide. So if we looked at something, say like, let's do So why don't you take a second and come up with the proper name for this guy, NiS2. Okay, let's take a look. So once again, we would want to identify sort of what we're dealing with. So nickel, which is a metal, sulfur, which is a nonmetal, so we know it's an ionic compound. Once again, we would then turn our focus to the metal part, which is nickel. And if you look on the periodic table, you should see it in the transition metal region. And that right there should tell you that this is a type 2 compound. And what that really should also tell you is I do need to use a Roman numeral here. So we need to figure out what that Roman numeral needs to be. In this case, we have just one nickel, and we're not sure what the positive charge is. So because of this, we would then focus in on the nonmetal, and we see S, which is sulfur. And S on the periodic table is also group number 6, which means it should have a -2 charge. In this case, though, we don't just have one sulfur, but we actually have 2 of those sulfide ions. And that means that we would actually have 2 of those -2s sitting out there. That means the overall negative charge here on the sulfurs altogether is -4, right? And that's really important because in this case, to balance out the charge, the nickel would have to have what type of charge? +4 to balance it out. And now that we have that worked out, we can now figure out our name, which would be the whole name of the metal, which would be nickel. Our Roman numeral here should be 4. And that again is not how many nickels we have, but it's the actual positive charge on one of the nickels by itself. And in this case, even though there are 2 of these anions, it has no effect in this name. So again, do not use prefix here. We just simply make sulfur into sulfide, IDE. So this would be nickel 4 sulfide in this case. Yeah. Question on that one? Now, when we do have names and we want to go backwards, right, which is another thing that we want to do, and we know it's an ionic compound, what we want to do is make sure that we just take the basic units that are present. So for example, if we had something, we'll just go with barium nitride. Let's also look at like something. Let's go with chromium 2 bromide. So if you have the name and you want to go backwards, it's important to also recognize what type of compound you have. Is it ionic? Is it covalent? So when we look at barium, we know that's a metal, and nitride is nitrogen, which is a nonmetal. So right off the bat, it tells us it's ionic. And that means that we're going to have a cation that's positive. We're going to have an anion that's negative. And when we put it together, we want to make sure that it equals 0. When you want to put it together, you simply just want to start with just the basic 2 ions and then put it together properly. So in this case, barium, which is group number 2 on the periodic table, has a fixed charge, and it should be a +2 charge. Nitride, which is nitrogen, which is group 5, should have what type of charge? It is a -3 in this case, right? So at this point, these are the 2 basic units basically that make up this guy when we put it together. Again, we're taking something that's positive, we're taking something that's negative, and we want it to equal 0. The simplest way to figure out how many of each of these you need is just to simply multiply those numbers together. So 3 times 2 is 6. So again, we just need to get each of those guys to 6. If it helps you, you could draw it out. So to get this negative guy to 6, we need 1 more, right? That gives us a 6. To get the positive guy to 6, we need a couple more here. And at that point, all you have to do is count what you got there. That's 1, 2, and 3 bariums. So you take barium with a 3, and that is 1 and 2 nitrogens, which means that would give us the proper formula in this particular case. Question on that one there. When we look at the next one, which is chromium Roman numeral 2, we see a couple things. That is a metal. Bromine is a nonmetal, which means it's ionic. So once again, we're going to have a positive guy and a negative guy. This is a type 2 compound because I see a Roman numeral, right? The also nice thing about this is I don't have to figure anything out because I should know the chromium has what type of charge. It does, and that's exactly what the Roman numeral means. It tells you it is a +2 charge. So there's really nothing to figure out for that. Bromide, which is bromine from the periodic table, is group number 7, which means it should have a -1 charge. So again, in case you can't figure it out, you could take 2 times 1, which is 2, right? So we need to get everybody to 2. That's already at 2, so we don't need any more of those. To get this guy to 2, we need 1 more. Now we just write what we did. So we got 1 chromium and 2 of those bromines, right? So we would have that number right there. Oh, okay, questions on that? Good. Other questions on that? Yeah. So here, let's try a couple more. Let's just make sure. Let's do lead to phosphide. What is the formula? And what is the name of something? Let's go with MnCl4. And we add 1 more or 2 more here just to make sure. Let's do with calcium. Let's do calcium sulfate and iron 3 hydroxide. All right, let's take a look at these here. So we'll start top here. So once again, we do see lead, which is a metal. We see phosphide, which is really phosphorus, which is a non-metal. So again, that tells us it's an ionic compound. We also see that lead has a Roman numeral, so we do know it's a type 2 compound. And also in this case, it also helps us not to have to figure out anything other than the lead here, which is Pb, should have a +2 charge. Again, that's what the Roman numeral there basically tells us. Phosphide, which is phosphorus from the periodic table, that is group number 5, which means it should be carrying a -3 charge. So once again, if we just simply multiply those 2 numbers, we're back to 6, which is a common combination. So to get the phosphorus to 6, we need a grand total of 2 of them. To get the lead, which has a +2 charge, to 6, we need 3 of them. And now we just write what we did there. So we got 3 of those guys. So that's going to be Pb3. And we have 2 of these guys, which would be P2 in this case. Yeah. Any questions on that one there? Coming over here, we see Mn, which is manganese. I'm going to spit that out, right? Hopefully. Cl is chlorine, which is a nonmetal. So again, this tells us metal, nonmetal, ionic. We look at Mn and we find it in the transition metal region of the periodic table, which pretty much tells us it's going to be a type 2 compound. Also, in this case, because we're writing the name, we do need to figure out the charge on it. So we do have just 1 of these guys, but we do know for sure that Cl is group number 7, which means it should have a -1 charge, and there are 4 of them. So if we just kind of write all 4 of those out, that's going to give us a grand total of -4 for the negative side. Again, to balance it out to 0, the Mn has to be +4 to balance it out. And again, at this point, we could just write what we wrote there. We have 1 Mn, and we have 4 of the Cls, and I'm writing the formula again, so I don't want to do that, do I? So I actually want the name in this case, but I would have wrote the formula correctly. All right. So now that we have the charge, we do want to write the name in this case. So we're going to use the whole name of this guy, which is manganese. The Roman numeral here will be 4 because of the charge on it. And even though we have 4 of those chlorines, it's just going to be chloride at the end of it. So that would be manganese 4 chloride. Once again, there's absolutely no prefixes ever in a really type 1 or type 2 compound. So you should not use any of those prefixes. Any questions on that one there? Good, yeah. Question on this one here is calcium, which is a metal. Sulfate here is actually a polyatomic ion, which is basically a negatively charged ion. So calcium, we want the basic unit of it. It is group 2, which means it has a +2 charge. Sulfate's one of those polyatomic ions on that list, which has a SO4 2-. So remember that sulfate, actually all these guys stay together and the overall charge is -2. So really what we're putting together here is +2 and -2, which means we just need one of each of those basically in this case. We're balanced and we would have CaSO4. Question on that one there. We look here, we see iron Roman numeral 3. So that tells us iron, which is Fe, has a +3 charge. We see hydroxide, which is also a polyatomic ion from that table, and that is OH- in this case. So once again, these two guys stay together and it has just a -1 charge. So really here we're putting together +3 and -1. So if you take 3 times 1 is 3, basically, is what we're looking for. So obviously the iron's at 3 already. So this guy means we need not 1, not 2, but we need 3 of those guys to give us a -3 charge. So when we put this together, it would be Fe. The other thing that we talked about is if you have more than one polyatomic ion and you're putting it into a formula, you do need to put parentheses around it. And the number on the bottom right of how many of those guys you have. Again, without the parentheses, it would be incorrect because you would have something that looks like this. And basically what that is saying is you have only 3 hydrogens and 1 oxygen, which is obviously not the case here, as you also have 3 oxygens in this case, right? So it's really important to remember more than one polyatomic ion, you need to put parentheses around it. With just one polyatomic ion like we had here, you don't need the parentheses. But if you have more than one, you do need to put the parentheses. Question on that one there. Lastly, here we have Ag, which is silver, which is a metal. We have NO3, which is nitrate, which is a polyatomic ion. This is basically silver. Now remember that silver is one of those 3 transition metals that actually does have a fixed charge. So silver is +1, cadmium is +2, and zinc is +2. So those 3 transition metals, although they're transition metals, do have a fixed charge of +1. In this case, the silver has +1. Nitrate is NO3-. So in this case, really, the silver, even though it's a transition metal, is a type 1 metal, which means we go back to our type 1 rule, which is we don't need a Roman numeral. We just use the whole name, which would be silver. And for any polyatomic ion, no matter how many you have, you just use the name of it, the whole name of it, and that would be nitrate. So this would be known as silver nitrate. And just like over here, this was called iron 3 hydroxide, even though in the formula, there are 3 of them. So it doesn't have any effect on the name. Question on type 1, type 2 compounds.